Today we'll talk about AI agent loop patterns, not what an agent is in theory and not the full anatomy of an agent. Here we focus on the practical part. How an AI agent runs step by step. Most modern LLM agents follow some version of the same cycle: sense, think, act, observe, repeat, finish. The model reasons about what to do next, calls a tool or produces an action, observes the result, and then decides whether to continue or stop. This is the foundation behind many agent systems: coding agents, research agents, RAG agents, customer support agents, automation agents, and multi-tool AI workflows. In this video, we'll go through the most common React-style loop patterns and when each one makes sense. If this helped, like and subscribe. It pushes the lessons to people who actually care about the topic, and you'll catch the next videos in this series. It costs you nothing, but it means a lot to me and my team. If something clicked or you have a question, leave a comment with your use case. I read comments, and they steer what I publish next. To learn more about me, visit this page. For agents, RAG, MCP, and related pages, visit this page. Same links are below in the description and pinned comment. Huge thanks. Your attention makes the work worth it for me and everyone behind the channel. Table of content. What agent loop patterns are: ReAct, Conversational ReAct, ReAct with description, multi-action ReAct, Iterative ReAct, ReAct with reflection, ReAct with memory, ReAct with planning, chain of thought plus ReAct, tree of thought plus ReAct, sandbox execution agent, ReAct with learning. Final takeaway. If you want more on agent anatomy, loop patterns, strategies, RAG anatomy and strategies, LLM engines, vector DBS, and MCP, the hub page is linked below. That's the map I use to tie the pieces together. An AI agent is not just a chatbot that returns text. It uses an LLM together with tools. Those tools can be APIs, databases, file systems, search engines, browsers, code execution, or other external systems. The important part is the loop. The model receives input, reasons about the next step, performs an action, observes the result, and then decides what to do next. That cycle is what makes the system feel agentic. A normal chatbot gives one answer. An agent can take multiple steps. It can search, inspect data, call a function, read the output, change direction, retry, ask the user, or stop when the task is done. So when we talk about agent loop patterns, we are talking about different ways to organize that repeated cycle. The basic pattern is ReAct, which means reasoning and acting. The loop is think to act, to observe, to repeat, to result. The model first reasons about what should happen next. Then it acts, usually by calling a tool. Then it observes the result of that tool call. That observation is important because it grounds the next step in real data. For example, if the agent searches a database, the database result becomes the observation. The model then uses that result to decide the next action. The strength of ReAct is that it creates a clear flow. The model is not just guessing from memory. It can interact with the outside world and update its next step based on what actually happened. The downside is cost and latency. Every extra loop means more model calls, more tool calls, and more time. If the prompt is unclear or the tools are badly designed, the agent can also get stuck calling the wrong tools again and again. So ReAct is the simplest useful pattern, but it needs clear tool contracts and good stopping rules. Example: what is the weather in Hoboken today, and should I carry an umbrella? Think: I need current weather data. Act: call weather API. Observe: rain expected at 3 p.m., 12 degrees Celsius. Think: since rain is expected, recommend umbrella. Result: yes, carry an umbrella today. The model did not guess the weather from memory. It used a tool, received real data, then reasoned on top of it. The next pattern is Conversational ReAct, sometimes called ReSpAct. This adds one important ability. The agent can talk to the user during the loop. The loop becomes sense arrow, think arrow, ask or speak arrow, think arrow, act arrow, observe, arrow, repeat arrow, final result. This is useful when the user request is ambiguous. Instead of guessing, the agent can ask a clarification question. For example, which database should I query? Do you want a short answer or a detailed report? Should I apply this change or only show the plan? This pattern improves trust because the user stays involved. It also reduces wrong tool calls because the agent can ask before acting. The trade-off is speed. More conversation means more round trips. That can be good for interactive assistance, but bad for automated workflows where you want the agent to run without interruption. Use this pattern when user confirmation or clarification matters more than raw speed. Example: find the best restaurant for dinner tonight. Input: find the best restaurant for dinner tonight. Think: best is unclear. I need preferences. Ask: what cuisine do you prefer and what city are you in? User: Italian, Hoboken. Think: now I have enough context. Act: search Italian restaurants in Hoboken. Observe: several highly rated options found. Ask: do you want casual dining or something upscale? User: casual. Think: filter based on preference. Final result: I recommend a casual Italian restaurant in Hoboken with strong reviews. Another variation is ReAct with description. The loop: think to, optionally describe what it will do or has done. To act, to observe, to final result. But the agent also describes what it is doing or what it has done. For example, I'm going to search the documentation. I found 3 relevant files. Now I'll compare the results. This is useful for transparency. Users do not want to watch a black box. If an agent is doing multiple steps, short status updates make the process easier to trust. This is also useful for debugging and audit logs. The risk is noise. If the agent describes too much, the experience becomes slow and annoying. Descriptions can also drift from reality if they are not based on actual observations. So this pattern is best when visibility matters: debugging, compliance, complex workflows, or user-facing automation. Example: fix the bug in my API where login sometimes fails. Think: I need to inspect authentication logic. Act: open login controller file. Description: I'm checking the login handler for potential issues. Observe: found JWT validation, mismatch in token expiration check. Description: I found a possible cause. Token expiry is not being validated correctly. Act: search documentation for JWT expiration handling. Description: comparing correct JWT expiration implementation. Observe: confirmed correct fix approach. Think: apply fix and update validation logic. Act: patch code and rerun tests. Description: I updated the validation logic and reran the tests. Observe: all tests pass. Final result: login issue fixed. Token expiration validation was corrected. In basic ReAct, the agent usually performs one action at a time. In multi-action ReAct, the agent can call multiple tools in one step. The loop becomes think to act. With multiple tool calls, to observe all results, to think again, to ... to final result. For example, the agent might search documentation, query a database, and calculate a value in parallel. This can be much faster than doing everything one by one, but it only works when the actions are independent. If one tool call depends on the result of another, parallel execution can create ordering problems. There is also more risk with side effects. Reading from 3 sources is usually fine. Writing to 3 systems at once is dangerous unless the workflow is very controlled. So multi-action ReAct is useful for independent lookups, parallel search, comparison, and aggregation. But for ordered workflows, keep the steps separate. Example: Get the latest stock price of Apple, Microsoft, and Google and compare them. Think, I need stock prices for multiple companies. Act, multi-action. Call API, get stock price AAPL. Call API, get stock price MSFT. Call API, get stock price GOOGL. Observe. AAPL, $190. MSFT, $410. GOOGL, $175. Think. Now compare values and determine highest and lowest. Final result, Microsoft has the highest stock price at $410. Apple is $190. Google is $175. Iterative ReAct is the normal ReAct loop used with deliberate repetition. The agent does not try to solve everything in one big step. It takes one action, observes the result, updates its understanding, and then takes the next action. The loop is think, to act, to observe, to think again, to act again, to observe again to result. This is useful when the task is unclear at the start. For example, a coding agent may first inspect the files, then read the relevant function, then check the error, then make a fix, then run tests. Each observation changes the next step. The benefit is control. The agent can adapt as it learns more. It does not need the full answer up front. The downside is latency. More iterations mean more model calls and more tool calls. So you need limits, max steps, timeout, retry caps, and a clear definition of when the task is done. Use Iterative ReAct when the agent needs to explore, debug, investigate, or solve something step by step. Example, my API returns 500 error when creating a user. Think, I need to investigate the error step by step. Act, call API endpoint to create user. Observe, 500 internal server error returned. Think, I should check server logs. Act, fetch backend logs for create user function. Observe, error shows, cannot read property email of undefined. Think, input validation might be missing. Act, inspect request body handling in controller. Observe, no validation middleware is applied. Think, fixes to add validation for request payload. Act, add validation middleware and redeploy. Observe, API now returns 201 created. Final result, bug fixed by adding missing request validation in user creation flow. ReAct with reflection adds a self-checking step. The loop becomes think, to act, to observe, to reflect, to maybe retry, to repeat if necessary, to final result. After the agent completes an action or attempt, it reviews what happened. It can ask, did this solve the task? Was the result correct? What failed? What should I do differently next time? This is useful when the first attempt might be wrong. For example, a coding agent might write code, run tests, see a failure, reflect on the error, and then try a better fix. Reflection improves robustness, but it has a cost. Every reflection step is another model call, and reflection is not magic. The model can still misunderstand the problem or overcorrect. This pattern needs clear stop conditions. Without limits, an agent can reflect and retry forever. Use reflection when quality matters and the task is complex enough that a single pass is not reliable. Example, fix the bug where my function returns NaN when dividing numbers. Think, I need to inspect the division function. Act, run the function with test inputs, 10 divided by 2, 5 divided by 0, 0 divided by 5. Observe, 10 divided by 2 equals 5, 5 divided by 0 equals NaN, 0 divided by 5 equals 0. Reflect, division by 0 is not handled, which causes NaN. This is incorrect behavior. Think, I should add a guard clause for division by 0. Act, update code to return 0 or error when denominator is 0. Observe, tests rerun successfully, no NaN values. Reflect, fix is correct and stable, no further changes needed. Final result, bug fixed by handling division by 0 cases properly. ReAct with memory adds persistence. Normal tool observations are temporary. The agent sees the tool result during the current run, but unless you store it, that information disappears. Memory changes that. The loop becomes think to act, to observe, to read, /write. Memory to ... to final result. Memory can store user preferences, previous decisions, summaries, task history, or useful facts. For example, the user prefers short answers. This project uses Next.js. This API failed before with this error. The previous solution was rejected. Memory helps agents work over longer sessions. It can reduce repeated questions and repeated tool calls. Short-term, episodic memory stores recent interactions within a session, like what just happened in the current task flow. Long-term memory stores stable, reusable knowledge across sessions, such as user preferences, project context, or recurring patterns. But bad memory is dangerous. If the agent stores something incorrect, stale, or too broad, it can poison future decisions. So memory needs structure, cleanup, scope, and sometimes expiration. Use memory when the agent needs continuity across steps, sessions, or users. Example, help me continue my API project. Think, I should check if I already know anything about this project. Read. Memory. Project uses Next.js. API previously had auth issues. User prefers short, clear answers. Act, load project structure. Observe, found NestJS backend with JWT auth. Think, I should store this new context for future use. Write memory. Current backend framework, NestJS. Auth system, JWT based. Think, now continue with relevant suggestion. Final result, I suggest improving JWT refresh token handling in your NestJS API. ReAct with planning adds a planning step before execution. The loop becomes input to plan to execute each step, with ReAct to observe to repeat, if necessary, to final result. Instead of jumping directly into tool calls, the agent first creates a high-level plan. For example, understand the request, find relevant files, inspect current implementation, make the change, run checks, summarize the result. Then each step can run its own think to act to observe loop. Planning reduces random tool use. It gives the agent direction and makes complex tasks easier to manage. The weakness is that plans can be wrong. If the first plan is bad, the agent can waste time following the wrong path. That is why strong systems often need replanning. After new observations, the agent updates the plan. Use planning for long tasks, multi-step workflows, research, coding, data analysis, and anything where order matters. Example, refactor my authentication module and make it more secure. Input, refactor authentication module for better security. Plan. 1. Inspect current auth implementation. 2. Identify security weaknesses. 3. Update JWT handling and password hashing. 4. Run tests. 5. Validate security improvements. 6. Summarize changes. Execute step 1. Think, I need to locate auth module. Act, open auth service and controller files. Observe, found JWT auth with basic password hashing. Execute step 2. Think, check for weaknesses. Act, review password hashing logic. Observe, passwords are using weak hashing, MD5. Execute step 3. Think, improve hashing and JWT handling. Act, replace MD5 with bcrypt, update token expiry. Observe, code updated successfully. Execute step 4. Think, verify changes. Act, run test suite. Observe, all tests pass. Final result, authentication module refactored with stronger password hashing and improved JWT security. Chain of thought plus ReAct means the agent uses more explicit reasoning during the think step. The loop is still think to act, to observe, to repeat, if necessary, to final result. But the thinking is more detailed. This can help with difficult reasoning, math, planning, or tool selection. The model breaks the problem down before deciding what action to take. The benefit is better accuracy on complex tasks. The cost is verbosity, latency, and privacy concerns. In many production systems, you do not want to expose or store raw chain of thought. Instead, you may show a short summary of reasoning while keeping internal reasoning hidden. So the practical idea is, use stronger reasoning when the task is hard, but do not expose every internal thought to the user. Example: a store gives 20% discount on a $50 item, then adds 10% tax. What is the final price? Think detailed reasoning. Original price equals $50. Discount equals 20% implies $10 off price after discount equals $40. Tax equals 10% of $40 equals $4. Final price equals $44. Act. Perform calculation step by step. Observe. Computed final price is $44. Final result. The final price after discount and tax is $44. Tree of thought plus ReAct is useful when one reasoning path is not enough. Instead of thinking in one straight line, the agent explores multiple possible paths. The loop is more like generate options, arrow, evaluate options, arrow, choose path, arrow, act, arrow, observe, arrow, repeat, if necessary, arrow, final result. For example, if an agent is debugging a production issue, there may be several possible causes: database problem, API problem, deployment problem, cache problem, or bad input. A normal ReAct agent may follow one path. A tree of thought agent can compare several paths before acting. This helps with complex reasoning because the agent does not commit too early. The trade-off is cost. Exploring multiple branches takes more tokens, more time, and sometimes more tools. It can also become messy if the system does not prune bad branches. So this pattern is best for hard problems where the first idea is often wrong. Debugging, planning, architecture decisions, research, and multi-step reasoning. Use it when quality matters more than speed. Example: my production API is slow and sometimes times out. Find the cause. Generate options. Branch A, database bottleneck. Branch B, API server overload. Branch C, cache misconfiguration. Branch D, external service latency. Evaluate options. Branch A, act, check DB query performance. Observe, some queries are slow, but not all requests affected. Branch B, act, check server, CPU, and memory. Observe, CPU spikes during traffic peaks. Branch C, act, inspect Redis cache, hit rate. Observe, cache hit rate is very low due to misconfigured TTL. Choose path. Cache misconfiguration is most likely root cause. Act, fix Redis, TTL configuration, and warm cache. Observe, API latency significantly improves, timeouts disappear. Final result, issue was caused by cache misconfiguration, leading to excessive database load. A sandbox execution agent is an agent that tests actions in a safe environment before touching the real system. The loop is, think to act in sandbox to observe, result to fix or approve, then apply safely, then repeat if necessary, then final result. This is common in coding agents. Instead of directly changing production code or running dangerous commands, the agent works inside a controlled environment, a test project, isolated branch, temporary file system, container, or restricted runtime. For example, the agent can write code, run tests, inspect errors, and retry inside the sandbox. Only when the result looks correct should it move toward the real target. The benefit is safety. The agent can make mistakes without damaging production data or user files. The downside is setup complexity. You need a reliable sandbox, good permissions, test data, and clear rules for what the agent is allowed to do. Use this pattern when actions can have side effects: code changes, database writes, deployments, file operations, or automation that touches real systems. Example: fix the bug in my payment API without breaking production. Think, I should not modify production directly. I will use sandbox. Act, sandbox. Clone repo into isolated environment and run tests. Observe. Tests fail on payment validation module. Think. I need to reproduce and fix the issue safely. Act. Sandbox. Update validation logic and rerun tests. Observe. All tests pass in sandbox environment. Think. Changes look safe. I can now apply to production branch. Act. Create patch and open PR with validated fix. Observe. CI pipeline runs successfully. No errors. Final result. Payment API bug fixed safely using sandbox validation before production deployment. The final pattern is react with learning. Here, the agent improves from experience. The loop becomes think to act, to observe to feedback, or reward to repeat if necessary. To final result, learning can happen in different ways. The simplest version is storing corrected strategies. For example, if the agent failed and the user corrected it, the system stores that correction and retrieves it later. A stronger version is fine-tuning, where feedback data updates the model. An even stronger version is reinforcement learning, where the agent improves from rewards and outcomes. The benefit is clear. The system gets better over time. The risk is also clear. It can learn the wrong thing. Bad feedback, noisy data, or weak evaluation can make the agent worse. So learning needs data hygiene, evaluation, rollback, and guardrails. For most products, start with stored strategies and feedback logs before jumping into fine-tuning or reinforcement learning. Example, fix my API login bug. Think, I need to debug login failure. Act, inspect authentication code. Observe, JWT token is not being saved correctly in local storage. Feedback, user reports previous fix attempt did not work. Learn, previous approach missed token persistence step in client-side logic. Think, I should update both back-end response and front-end storage handling. Act, apply fix and update client logic. Observe, login now works correctly. Update memory/strategy. Always ensure JWT is stored after successful login response. Check both back-end response and front-end persistence. Final result, login bug fixed with improved token handling strategy learned for future cases. If this helped, like and subscribe. It pushes the lessons to people who actually care about the topic, and you'll catch the next videos in this series. It costs you nothing, but it means a lot to me and my team. If something clicked or you have a question, leave a comment with your use case. I read comments and they steer what I publish next. To learn more about me, visit this page. For agents, RAG, MCP, and related pages, visit this page. Same links are below in the description and pinned comment. Huge thanks. Your attention makes the work worth it for me and everyone behind the channel. Conclusion. The main idea is simple. You do not need every agent pattern at once. Start with basic React. Think to act, to observe to result. Then add only what the product actually needs. Add conversation when the user must clarify. Add description when transparency matters. Add multi-action when independent tools can run in parallel. Add reflection when quality needs retries. Add memory when context must persist. Add planning when the task is long. Add stronger reasoning when the task is hard. Add learning only when you have feedback, evaluation, and rollback. Agent design is mostly about trade-offs, speed versus quality, automation versus user control, memory versus stale context, planning versus flexibility, learning versus safety.